the next one is about scaling row operations. This property has been selected by the textbook as the three basic properties to derive the determinant function properties. But for us, that's just a consequence of our choice of SM1 to SM3. And this time, I think I will allow alpha to be 0. Okay, so it's a little bit extended. All right. So as we say that this scaling is a row operation, so we we multiply a constant, a scalar alpha, on say the iso, right? This is our notation, right? So this is comes to determinant of U1 alpha UI UN. So probably I change a little bit. And in normal, in ordinary scaling, we use the scalar which is non-zero. Okay, which is non-zero. But for here, I need to use zero scalar. Okay. All right, and this is alpha determinant U1, UI, UN by the linearity on any row. Okay, and which is theorem for 1.B we mentioned before. So this is just linearity on any row. Here it's just on the iso. So if alpha is 0, of course this is 0. And if alpha is 0, this row is 0. So we have 0 property 4. Oh, okay. Here, theorem. Oh, okay. Before that, we give a remark. Determinant of CA. If you multiply a scalar with a matrix, a square matrix A, this is just Cn power determinant of A. Because that you multiply C with each row of A. Okay? You multiply with each row of A. Okay, maybe I do it. Okay, and then C. So by the previous property, so this is the property 4.1.3, and this is so Cn C square so finally okay. So it's about zeros, the determinant of if one of the rows of the matrix A is the zeros, then the determinant is 0. So the proof is easy because determinant of U1 zero vector UN is determinant of U1 zero vector UN. So zero vector can be expressed as zero scalar multiplication with zero vector again. And this is 0 determinant of one. So 0 times anything is 0. Okay. And here we apply we are using property 4.1.3. Okay, there. Property 4.1.1. Triangular matrices. Determinant of an upper triangular of 0 here and everything. So this is everything, but the lower parts are zeros. Okay, so this is the upper triangle matrix. Um, so the determinant of such an upper triangular matrix is the product of its diagonal entries. And this is the same for lower triangular. Okay. So this one is upper triangular matrix. And this one a lower triangular matrix. So we will work on the upper triangle because for the lower triangle case will be the same. Okay. So let's see. All right, so we have two cases. Case one, all diagonal entrances, AII, are non-zero. Okay, so they are non-zeros. Alright, so A11, which they are all non-zeros. Right, so then if we have non-zeros, we can eliminate all the entries above the diagonal entries by replacement law operations, right? Replacement law operation. Let us do the elimination. So that all the entries here will be eliminated. Okay. So then we can eliminate by Gaussian elimination. Okay. We can eliminate triangular matrix into a diagonal matrix by replacement row operations. Okay. As follows. So determinants A11, A22 up to ANN equal to determinant A11. So ANN, and these are all 0. And minus 1 and minus 1. Okay. So you can use the last one, that's ANN, to eliminate all the entries above it. Okay. by the row replacement. But as we know, in theorem, I proved the last Friday. Yes. With the replacement row operation, we will not change the determinant value. Okay. So we will keep the identity here. So the determinant of this matrix is the same as the determinant of this matrix after the elimination by replacement operations. Okay, so we can do so. Right, so continue to do so. So it becomes the determinant of A11, A22 up to ANN, and they are all zeros. Okay? Any questions? Just by the replacement operation. And every replacement operation will not change the value of the determinants. Okay? So we can do so. Now, you can apply the scaling row operation so that all bilinearity, that's all fine. So this is not to A11, determinant of 1, A22, and then ANN, 0, 0. Okay? So the first row can be regarded as a scalar A11 multiplied with 1, 0, 0, 0, 0. Okay? And so this is by scaling or by the linearity, that's fine. On any row of the determinant function. Okay. So continue to do so. We have A11, A22 up to ANN, and the determinant of the identity. So this is the identity matrix, and its determinant is equal to 1 by xn number 1. Yeah. So this is A11, A22 to ANN by xn 1. Okay, so if all diagonal entries AII are non-zeros, then the determinant of this upper triangle matrix is equal to the product of its diagonal entries. Okay. Any questions? All right. So no question. Case number 2. So there is a diagonal entry which is 0. Okay, so that is a diagonal entry which is 0. Okay, so we let U be the reduced row echelon form of the triangular matrix A. Okay. So okay, maybe I will give you more intuitive way of proof. So let me take an example. For example, A is equal to like right? So it's an upper triangle, and this entry is 0. Right? So there is a diagonal entry which is 0. Okay. Maybe I change it a little bit. Say 1. Okay. Maybe it's better. Now we look at the we partition the matrix into two. And look at the submatrix B here. So it's 2 by 3. It's 2 by 3, right? So if we apply the elementary operations to make it go to its reduced low echelon form, now you can see that this submatrix in here, you have at most 2 pivots. Right? You have at most 2 pivots. Because each row at most has one pivot only, right? So that in here you have at most 2 pivots, so that at least one of the columns here is no pivot. Okay, just from the dimension, this is 2, this is 3. Okay. So that these 3 columns, because we don't have enough pivots, so one of the columns has no pivot. Then, so these 3 columns, 1, 2, 3, these 3 columns must be linearly dependent. Okay? And the rest of them, they are all 0. So these 3 columns must be linearly dependent. Alright? So they must be linearly dependent. Alright, so let me describe it. So without loss of generality, we assume that aii equal to 0. Okay? So then A can be described in here. This is A11 up to AI minus 1. I minus 1, I minus 1. So minus 1, yeah. So here, I'm sorry. Here is I minus 1 and I. Okay. And oh. I minus 1, I minus 1, and the next one is I minus 1 and I. Okay, great. And we have 0 here. And we have I plus 1, I plus 1, that up to A and N. Okay, this matrix. So the diagonal is here, the diagonal, yeah. And we have 0 up here, and this is 0, 0. Okay. So that we have here. And this part is called the B matrix. And all zeros. Okay. So this submatrix consists of all 0 entries. And the dimension of B is, here we have I minus 1 rows, and we have I columns. I minus 1 rows. Okay? So the dimension is I minus 1 times I. Right? Any questions? So compare the A here. So this is 2 and this is 3. Okay. So B is I minus 1 times I. Okay, the matrix they are different here. Any questions up to now? Right, so now we'll now look at the submatrix since the submatrix B of A, right, it's I minus 1 times I. There is a column of B having no pivot by theorem 1.3.7. Okay. Right? Because the rank is the minimum, right? Because the rank is the minimum of the row and the column. So as I explained that because B has I minus 1 rows, so the B has at most n minus 1 pivots. But we have I columns, So this is one of the columns B having no pivot. And then the columns of B are linearly dependent. Okay? By theorem 1.3.12. Okay? So we learned that 1.3.12 before. So if the columns, one of the columns has no pivots, then these columns must be linearly dependent. All right, so which implies that the first I columns of A, because the first I columns, the difference from the first I column with the constant of B is that here we add all zeros. Okay. So the first I columns of A are linearly dependent too. And then the columns of A form a linearly dependent set. Okay, because when the first I columns are linearly dependent, then of course if you add more columns into it, these n columns must be linearly dependent. Okay, so we know that, maybe. Now, if the columns are linearly dependent, so that's there is a column of A having no pivot. Okay. Again, by theorem 1.3.12. Okay. Because 1.3.12 tells us that if a matrix, if each column has a pivot, then the set of all columns form a linearly independent set. So that is even only a condition. Okay. So we say that P implies Q. And so that this is equivalent to, so if a matrix, if the columns of matrix form a linearly independent set, then there is every column has a pivot. This is an economic condition. So that if the columns of matrix are linearly dependent, then at least one of the columns has no pivot. Okay, no pivot. All right, so we use the same theorem twice. Okay. Okay, so now we have no pivot. All right, so this implies that the rank of A is less than n, and this implies that U the reduced row echelon form U is a zero row. Okay. Right. So you know, so if the ring is less than n, so that means that one of the row of A has no period. Okay. Then the reduced, actually any row echelon form, not necessarily reduced, but any row echelon form of U has a zero row. I forgot the theorem, but because I didn't put it here. Okay, so that is the story, right? From the consequences that when we have a zero entries here, by the discussion, we know that the reduced row echelon form U of the matrix A has a zero row. Okay, but U is obtained by applying row operations, so that where E1, E2 up to Ek are of types Eij, alpha, or Si, beta, and the beta not equal to 0, or Pij. Okay. So the reduced echelon form is obtained by applying elementary operations. That means that we apply elementary matrices or scaling matrices or permutations. So we can apply the placement, the elementary matrix, scaling matrix, or permutation matrix there. Okay, so we have that. Okay, now since U contains a zero row, right? So the determinant of U is 0. Okay? But this is determinant of Ek, E2, E1A. Now, Ek is either a permutation matrix, you are doing the row exchange, or doing the placement operation, or doing the scaling. So you have Ck and determinant of where Ck is equal to 1 over beta or minus 1. Or minus 1. Okay? 1 corresponding, if you are doing the replacement operation, then Ck is 1. If Ek corresponding to a scaling, then Ck is beta. Beta is not equal to 0. And if Ek is row exchange, then you have to Because if you do no exchange, then you have to multiply with -1. You have to change the sign. So ck can be only 1 or beta or -1, not equal to 0, okay, etc. So that you can do it. So ck, c2, and c1, and determinant of A. All right. So specifically, so Ci where Ci is not equal to 0 for all I from 1 to 10 specifically. Now C2, C1 up to C, they are non-zero. Okay. But the product equals 0, so this implies that determinant of A is equal to 0, and this is A 1 1, A 2 2, up to AII. To ANN. And remember, AII is 0. So we have done. Okay. So finish the proof. Okay, so again, the determinant of A is still the product of the diagonal entrances. Okay, and of course, because one of them is 0, so the product is 0. Okay. Actually, if you look at the example, you can see that if we do the no operations or we do Gauss-Jordan elimination, actually, finally, you can see that we will have all 0 rows apparent from this example. Why? Because in here, for the last columns, this one will eliminate this one. So when we eliminate this one, when use -2 to eliminate the 4, then the last row becomes to the 0. Okay. So at each example, it's very easy to see you will obtain a 0 row when you reach to the reduced row echelon form. Okay. But how do we prove that in a rigorous way? Then we have to make a statement like this one. It's long, but I try to give you the elementary proof. Because everything here is about the columns and the rows. So what we need is a result from the chapter 1. So chapter 1 is the very basic chapter because it's about Gauss elimination, row operations. Okay. Right. So everything can be traced back to the elementary operations. Any questions? Alright, so if there's no questions, then I move to the next theorem. It's theorem 4.1.4 plus 5. So I combine theorem 4.1.4 and 4.1.5 in the textbook together. Okay. It's about invertible matrices. determinant A is non-zero if and only if A is invertible. Alright, so this is the first, and again, if and only if the rows or columns well, maybe to show if and only if the rows or columns of A form linearly independent. This one, A is invertible if and only if the rows of A form a linearly independent set, if and only if the columns of A form a linearly independent set. I think it's in the statement of the invertible matrix theorems in chapter 3, right? So we already know this fact. Okay, so the proof is like this one. So let U be the reduced row echelon form of A. Okay, so U reduce row echelon form of A. Right, so we will prove that suppose A is not invertible, okay, then U has a zero So because determinant A not equal to 0, so we assume that determinant of A is not 0, then we have to show A is invertible. Okay, so this is P, this is Q. Okay, and this part, if we want to show P implies Q, this is the same as negative Q implies negative P. But negative Q is that we assume, suppose A is not invertible, right? So A is not invertible. Then if A is not invertible, then the reduced row echelon form is a 0. Right? In chapter 3, we know that. So this implies that the determinant of A is 0. Okay? The reason is the same as we did here. Because U is a 0, so determinant of U is 0. And the U can be obtained by applying elementary law operations on A, so that is 1. Okay? And for each elementary law operations, the effect is that you multiply with a constant ck. This ck is either 1 or a non-zero scalar or -1. So that finally we have ck P1 times determinant of A. And because ck, C2, C1, they are all non-zero, but the product is 0, so determinant of A is 0. So the idea is the same. Okay? So we can, the reason is here. Right? You can go to C. It's not necessary for me to repeat the process again, right? So, maybe I can make a statement here by seeing a proof in the previous theorem. I think in the previous the second part, I'm seeing the second part of the proof of the property (4.1.1). Okay. So if A is not invertible, we know U must has 0. Okay. So the determinant of A is 0. And the reason is why it has a 0, you can remember the discussion in chapter 3. Because if A is invertible, we know that the columns of A or the rows of A are linearly independent. So if A is non-invertible, then the rows of A form a linearly dependent set. And the theorem in chapter 1 says that if the rows are linearly dependent, then any row echelon form has a 0. Okay, so that in particular, the reduced echelon form U has a 0. Okay, and so it implies that the determinant of A is 0. So we finish because that starting from non-invertibility, we prove that determinant A is 0. Right? So we prove the negative P. So we finish. The other direction, so you can say that, or you can say this is a contradiction. A contradiction. What? To the effect. If you start with this one, and you assume this is non-invertible, we get a contradiction. So this assumption is invalid. Or you can logically just proving this one. Okay? So you can get rid of the contradiction to determinant of A not equal to 0. If we can prove this one. Alright, the forward direction. We assume that A is invertible. So since A is invertible, we know that U is the identity. Okay? So in chapter 3, we know the reduced low echelon form of any invertible matrix should be the identity matrix. The determinant of A it's alpha determinant of U. Again, like this. Because determinant of U or determinant A, they have related or with alpha not equal to 0, right? As we know, because that to obtain U, we're applying elementary law operations. When we apply law operations, every time we multiply with a non-zero constant. So finally, we have the relationship. Determinant A is equal to alpha times determinant U. Okay, and alpha is not equal to 0. So this is alpha, determinant of I. So this is alpha, not equal to 0. Okay. So we have done. So the basic idea always here, if we are using the reduced low echelon form of a matrix, a square matrix A, remember we can reach to the reduced echelon form by applying an elementary law operation. Means that we can apply the replacement operation, we can apply the scaling operation, or we can apply the row exchange. Right. So let's take a break for 5 minutes. All right, the last theorem I want to prove in the first section of chapter 4 is about determinant of elementary matrices. All right, so determinant of Eij alpha is 1. Okay, determinant of the scaling is alpha, and the determinant of Eij minus 1. And the proof is simple. You can see that determinant of Eij alpha, if we think about that, is the replacement operation on the identity matrix. Okay? So as we know, to obtain this EIG alpha, we just apply the replacement operation on the identity matrix. But as we proved, to do the replacement operation on a matrix is the same as the determinant without change the determinants of this matrix. And by axiom number 1, this is 1. Okay, so we have that immediately. Okay. And determinant of Si alpha, the scaling, right? It's Si alpha on the linear matrix, and this is again alpha, determinant of In. So this is alpha. And determinant Ij is determinant of dot exchange on the linear matrix. So this is -1 minus. So we change the sign of it. Okay, so it's done. So everything is very straightforward, right? We just because what we need has been proved already there. Yeah. So we know the behavior. How do we change the determinant after applying the replacement operation? By applying the replacement operations, then we will not change the value of the determinant. And for we change two rows, then we will change the sign. Okay? Yeah. And by scaling, then we will multiply the scaling factor alpha. Okay. So everything is just layer, all right? There. We just stayed out on it. And so I think so the final word is that so please read theorem 4.1.6, 4.1.7, and 4.1.8 in the textbook. They are just simple theorems. Okay, so I move forward to the second section on the determinant function. Remember, up to now, we haven't proved the existence and uniqueness of determinant function yet, right? Not yet. We just proved a lot of consequences if we have three axioms on the determinant function. Axiom number 1 saying that the determinant of the identity matrix is 1. Okay. Axiom number 2, we have linearity on the first row. Okay. Axiom number 3 is that if we exchange two rows, we will change the sign of the determinant. So we have only these three simple axioms. And from these three simple axioms, we derive many consequences here. Okay? Including the three basic properties proposed by the textbook. Property 1, property 2, and property 3. Okay? We already proved all of them. For example, we spend a lot of time to prove that the determinant of a triangular matrix is just a product of their diagonal entrances. Right? So we spend a lot of time on that. Okay. But everything just by doing row operations, right? So we actually doing so. And so the next section, 4.2, is about properties, further properties of determinant. Okay. So first of all, I will give a lemma as a starting point, 4.2.8. For two n by n matrices, A and B, the product is invertible if and only if both A and B are invertible. Okay? So we start with such a lemma. Alright, so proof. Forward direction. Right, since A times B is invertible. Okay, since A times B is invertible, there exists an n times n matrix C such that A, B, C equal to the identity. Okay? And C, A, B, the identity. Okay? Because it's interval, right? So there is an inverse which is the right inverse as well as the left inverse. Right? So we do that. But this implies A by association. Okay? So now we solicited B and C first. So that means that A is right inverse. So that means that A is invertible. Because we have shown in chapter 3, if a square matrix, if a square, I have to emphasize square matrix. If a square matrix has a right inverse, then this matrix should be invertible. And the right inverse must be also the left inverse. Similarly, B has a left inverse, so B is invertible. Okay. Any questions? All right. So here I didn't specify the specific reasons. Just orally explain. So if you need to make a remark, you make by yourself. Any questions? Alright, so this is forward direction. So when AB is invertible, then we prove that A is invertible and B is also invertible. Forward direction. Since A and B are invertible, so we have A inverse equal to A inverse A equal to identity, B inverse equal to B inverse B equal to identity. Right? So we have that. Thus, we just claim that B inverse A inverse, but with the reverse direction, is right inverse of A times B. Why? By association. Okay? So So we use the associativity of metric multiplication. And this is A, identity, A inverse. So this is A inverse, and this is I, and with none. Okay, so that this one is a right inverse of A times B. And A times B is a square matrix again. So whenever a square matrix has a right inverse, then this square matrix is invertible again. Okay, so okay. Now, okay, so we go to another lemma. It's 2.4.2.1. Okay. Determinant Bij alpha A is equal to E determinant of Bij alpha, determinant of A, determinant of xi alpha A equal to determinant of xi alpha, determinant of A, and the determinant of Bij equal to determinant of Bij and determinant of A. Alright, and the proof. Follow from this result follows from okay, maybe I just write down here. So this is by property 4.1.2 and the theorem 4.1.d. Okay. And the scaling is by 7. And property 4.1.3 and theorem 4.1.3. This one. And the last one is by xm 3 and theorem 4.1.3. So this lemma is actually just all the many concepts we mentioned before, because that we operate on A by a replacement operation. We will not change the sign, so it would be equal to this one. But this, the determinant of this one is 1, right? Already. So just move to here. Okay? And then when we do the scaling, we multiply with alpha. Alright? But alpha is just equal to the determinant of this one. Okay. To do the row exchange, we change the sign. But -1 is just the determinant of Pij. Okay. So we just put everything here together. Okay? And it is the basic types of about determinants of the multiplication of two matrices. So if one of the matrices, because we are considering the determinants of the product of two matrices. But if one of the matrices is just elementary matrix, or the scaling matrix, or the permutation matrix, then this determinant is the product of the respective determinants. And that is the starting point to prove a general result later on. Okay, so so you can think about that. This is just a summary. Okay, so now I will state this result. Okay, so that would be here, 4.2.2. Okay, suppose that we have two n times matrices. So we have two square matrices. Then the determinant of their product, the determinant of their product is the product of their respective determinants. Okay. This is what we want to prove. So when we see this lemma, you can see that the results of this lemma are just special cases of this general theorem. Okay. And on the other hand, we will use this lemma to prove that. Okay. So even though they are just special cases, right, of this general result, but it's a very good starting point for them. Okay, good. Well, so we have two cases. This is one. A is not invertible. If A is not invertible, by our lemma here, if A is not invertible, then A times B must be not invertible too. Otherwise, because if AB is invertible, then A must be invertible. Okay. So if A is not invertible, then AB is not invertible. Two. So determinant of A is 0. Okay. And determinant of AB is 0. By the invertible matrix property. Okay, so that is theorem. Which number? 0.1, 0.4 plus 1. Okay? We prove that for the invertible matrices. Okay. So A is not invertible, of course, determine that A is 0. AB is not invertible, so determine that AB is 0. Okay? So that determinant AB is 0 becomes to 0 times determinant of B, and this is determinant of A times determinant of B. Okay, so we complete the first case. So A is non-invertible, then we prove that this is true. Okay. No matter what is B, okay, just A is non-invertible. So we prove that this is the case number 1. Case number 2. A is invertible. Alright? So that the reduced row echelon form of A is the identity. Okay? Because A is invertible. And we can obtain the reduced echelon form by applying elementary operations. So Eij alpha, Si beta, and Eij. Right? So we can do that. Now the same sequence of elementary matrix can apply to AB. Okay, can apply to AB. Now, so this is E1, EK, E2, E1A, and the B. So this is identity B, and so this is B. So now when we apply the same sequence of elementary matrices, or the same sequence of elementary row operations on this product, okay? We will end up with the matrix B. Now, the determinant of EK, E2, E1, A is equal to the determinant. So now, determinant I, so this is 1. Alright? Now, we'll apply lemma. When the matrix here is elementary matrices, then we can split, right? So we can separate them. And so in the left-hand side, this one will go to determinant of EK and determinant of EK minus 1, E2, E1A. Okay? So now EK can move up. And then so we can do it up to determinant of EK. Determinant of E2, determinant of E1, and the determinant of A. So the left-hand side, this determinant becomes to a product of determinants, EK, up to determinant E2, determinant E1, and determinant A. Okay? You can see that? So by applying by lemma, to 4.2.1. Okay? So the left-hand side here. All right, so that conclusion is that determinant of EK, that determinant of E2 here. Okay, so from here we get okay. Now from this identity, so similarly, okay, we have E determinant of EK, the determinant of E2, determinant of E1, determinant of AB equal to determinant of B. Okay, so determine, so you get what? Any questions? So these two results is by applying the lemma repeatedly, right? We apply the lemma repeatedly. Now we divide the rate, right? Right, okay. Divide the rate equation by the green equation. The green equation, you see, this is non-zero, 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 everything is non-zero, okay? Why? Because A is invertible, so the determinant is non-zero. Okay, so we have the rate divided by the green. Okay, I'm sorry you don't have colored pens there. Never mind, right? Okay, so that so we have, when we do that, we can cancel common factors, right? So that we have determinant AB divided by determinant A equal to 1 here, and the determinant of B. Perfect, right? Now, okay, just do the division. And immediately you have the result. And we have done. So it turns out the proof is very easy, right? At the first, it looks hard. Okay, it looks hard, but when we apply no operations, it becomes easy. Questions? Observations. Observations on elementary matrices. First observation 1, 1, 2, 4 alpha. For example, we consider, say, 5 and 5 matrices, just for the 1, 0, 1. How about the transpose? So the next question is about the transpose of this elementary matrix. So when we do that, we take the transpose, we find that this is and what is that? It's actually you multiply the second row with alpha and add to the first row. So this is actually see observation, right? The transpose of this elementary matrix E to 4 alpha is indeed you exchange 2 and 4 to 4 2 here. So this is another elementary matrix, another one. And so the determinant of E to 4 alpha transpose. So if we want to know the determinants of the transpose of this one, is the determinant of E for 2 alpha transpose. Okay? And which is what? Oh, sorry. No transpose. I'm sorry. So this is equal to 1, and which is determinant of E to 4 alpha without transpose. So the determinants of the matrix and the determinant of its transpose have the same value. Right? It's about the observation. How about scaling? For example, scaling. So this is 1, 0, 0, 0, 0, 0 beta, 0, 0, 0. Alright? So it's transpose. Well, because this is a diagonal matrix, so the transpose will not change at all. So this is S2 beta. Okay, so the conclusion is that S2 beta transpose is equal to beta is equal to the determinant of S2 beta without transpose. But so again, doing the transposition will not change the determinants for the scaling matrix. How about the no exchange or the permutation matrix? So P to 4, so it's 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. So you exchange the second and the first row on the identity matrix to get this one. And then you look at the transpose of this one. You find that the transpose of this one will remain the same. Okay? So you will so this is P to 4, same. So the determinant of P to 4 equal to identity equal to determinant of transpose is equal to determinant of P to 4 and which is minus 1. Okay, so these three special type of matrices will not change the value if you take their transpose. Okay. So that is the explanations. Alright, and so there are observations on 5x5 elementary matrices. Okay? But as you can see that it is a general result. So let me just state it. Lemma 4.2 point B for elementary matrices. So we have determinants of Eij alpha transpose is equal to determinants of Eij alpha, and the determinants of Xi beta transpose is equal to the determinants of Xi beta transpose. Determinants of Pij transpose equal to the determinants of Pij. Alright, so we have this. And our target is that, so now we are able to prove the theorem for any n by n matrices A on any matrix. That's matrix A. Determinant of its transpose is equal to the determinant A. Alright, I just give a few words and then we'll complete the proof next week. Next Friday, not this Wednesday, we will have University Sports Day. First, note that A is invertible. If and only A transpose is invertible. Right? This is a result, I think it's in chapter 3. I think the direct proof, maybe I will give you the reason, is that if you look at that, right? So if when A is invertible, so it has inverse. And then when you take the transpose, the transpose of the identity matrix itself, right? And so you can see the transposition A minus 1 T AP equal to AP A minus 1 T is identity. So it shows that A transpose is invertible because it has right inverse, it has left inverse, and also we know the inverse of the transpose is equal to the transpose of the inverse of A immediately. Okay, so that is a little bit review of the results in chapter 3. Okay, so we have that. Alright, so I will complete the proof of this theorem. Alright, because we have already the temperature here. And this is our temperature. Okay, because the result is true for elementary matrices here, like this. Okay, and so I will assign recommended access, even though we don't have quiz next Wednesday. Okay. All right. So I'll see you next Friday. Okay.